All right, so we're getting ready for our final. This is the Unit 2 review. This is going to be forces in one dimension. If we got our key points, we need to be able to understand these things. When is a system in equilibrium? We got to be able to draw free body diagrams, and we need to know Newton's three laws. The first law, the law of inertia. Um, we need to know the second law, which is force equals mass times acceleration. And the third law is equal and opposite forces. So if we look at question one, a spring exerts a force of 6 newtons on a cart. If the cart's mass is 30 kilograms, what is the acceleration of the cart? So, force equals mass times acceleration. We could plug these numbers in. 6 newtons would be the force. Our mass is 30 kilograms, leaving us with acceleration. Some of us are having trouble with equations like this. I want to remind us we're solving for our variable acceleration here. So we want to get that by itself, so we got to do everything we can to get that A isolated by itself. So if we're multiplying by 30 here, the opposite of multiplying by 30 is dividing by 30. This would cancel out, and our acceleration would equal 6 divided by 30, or about 0.2 meters per second squared. We want to make sure we're writing our units down. Question number 2, a 20 kilogram bucket hanging from a rope attached to the roof is being lifted at a constant velocity of 1 meter per second. Calculate the tension on the rope. So if the velocity is constant, if the velocity is not changing, we could think back to our velocity time graphs. If our velocity is not changing, the slope there is 0, which means our acceleration is 0 meters per second squared, meaning there is no net force. So the tension, there's only two forces acting here, the force of gravity and the force of tension, and they have to be equal and opposite. So if the force of gravity equals 20 kilograms times the acceleration of gravity, 9.8 meters per second squared. So it's going to be negative because it's pulling downward. That would be negative 196 newtons. That means our force of tension has to cancel that out. So it would be positive 196 newtons. So a little bit of a tricky thing to remember. It doesn't matter if it is still this bucket or whatever the velocity is. If it's constant, your acceleration is 0. Excuse me. Next one. Draw a free body diagram of a 90 kilogram person standing on the ground. Calculate all the forces on the person and state if they are in equilibrium. We basically did that with the bucket here. We got this person. They're on the ground. We know they are experiencing gravity. And in this case, gravity is going to equal their mass, 90 kilograms, times the acceleration from Earth, negative 9.8 meters per second squared. And we can calculate gravity right here. Negative 882 newtons. Then we are going to have, they're standing on the ground. The ground has to exert a force up to make sure they are not flying through. And because this person is not accelerating, they are in equilibrium. So we are going to say they're in equilibrium. That means our F net equals 0. And then I'll write an equation out here for you. So F net needs to equal all of our forces combined together. So that's going to be the normal force plus the force of gravity. So we could plug these two numbers in here. 0 equals our normal force plus negative 882. So if, the normal force plus negative 882 equals 0, that means our normal force has to equal positive 882 newtons to cancel out with our gravity. And lastly, we got a question. A 10-kilogram bucket tied to a rope is lifted to the top of a 20-meter building at a constant acceleration. So in this question, we do have an acceleration. The bucket started from rest at the bottom of the building and took 50 seconds to pull to the top. What is the tension on the rope? So I like to draw free body diagrams first. So we'll draw a free body diagram here. We got the force of gravity pulling us down. We got the tension. The tension is going to be, I hope I drew it. The tension is going to be bigger than the gravity in this case because it is accelerating upward. It is slightly bigger here, but we'll draw a bigger arrow. There we go. And then our net force is going to equal the tension plus the gravity. The first thing I want to do is, find my net force here. My net force is going to be the mass of that bucket times my net acceleration. And I'm going to use these equations here to find my acceleration. So if I look at my information, the rope is being lifted to the top of a 20-meter building at a constant acceleration. The bucket started at rest at the bottom of the building and took 50 seconds to go up. So my delta x, and we'll just write these off on the side. My delta x, my change in position, is going to be from 0 to 20 meters, 20 meters. My initial velocity is at rest, 0 meters per second. My time is 50 seconds. I am not given my change of velocity, so I am not going to use this equation. I'm going to end up using this equation. I got my delta x, and in general, if you're given position, probably using this one. If you're given the velocity, probably going to use this equation. So we got delta x. We're going to be using this equation. So let's start plugging everything in. We'll write it down again, just to keep everything nice and neat. We got 20 here equals, this becomes 0 because our VI is 0, so we'll just put a big 0 there. 1/2 times our acceleration. I'm going to write it as a decimal because it's a little bit neater. 1/2 acceleration times time squared. Time is 50. Wow, that's going to be a big number there. Okay. So I'm going to kind of simplify this. So 50 squared, I'll put the calculator on screen. 50 squared equals 2,500. And I got to multiply that by my 0.5. So times 0.5. I would get 20 equals 1,250 times my acceleration. This bucket's going to be going very, very slow, but it's going to be very, very safe. So that is a positive thing sometimes. So we divide both sides by this large number here. And we get our acceleration is 20 divided by 1,250, or an acceleration of 0.016 meters per second squared. So a very, very, very minor acceleration here. So from that, I could plug that back in up here and figure out what my net force is. I'll do it down here. My net force equals my mass, 10 kilograms, times my acceleration, 0.016. And, just move the decimal over one spot, 0.16 newtons. Not a lot. And we could plug that into this equation now. 0.16 newtons. And then gravity, always easy to calculate here. We got mass times the acceleration of gravity, 10 kilograms, negative 9.8 meters per second squared. That is going to give us negative 98 newtons. Wow, this acceleration is almost a rounding error here. So plus gravity, which is negative 98. So the force of tension, we'd add 98 to both sides. The force of tension is going to be 98.16 newtons. Look at that. It's just barely more than the gravity. All right, and that concludes our Unit 2 review.